Okay, Hector.
Yeah.
So we're at 7:05. We cut a few minutes off to make sure that others could join us. So I will introduce you. So welcome, everyone. This is Hector Munoz-Avila's invited talk at the start of the second session today of our workshop on RaD-AI at AAMAS 22. And I'm delighted to introduce Hector. He has been a longtime colleague working with me in topics that have ranged over many areas, including that of goal reasoning. And today, as you see, Hector is going to be specifically focusing his talk on rebel agents. He, in fact, worked with one of my earlier colleagues who was his PhD student, Alexander Coleman, on the topic early on. And so that was very much inspiring me to continue work with Alexandra when she worked with me as a postdoc. So Hector, thank you very much for joining us and look forward to your talk.
Thank you, David, and thank you for having me. Good evening, good morning, good afternoon, wherever you are. My name is Hector Munoz-Avila, and today I will talk about rebel agents towards safety-informed agents with goal reasoning. I call this a blue sky talk because many of these topics that I will be talking about are really ideas rather than report on existing work. This work is in collaboration with a number of colleagues and the students who are listed there. This work has been funded by the National Science Foundation and the Office of Naval Research. I have to do a disclaimer: any opinion, findings, and conclusions or recommendations in this presentation are those of mine and are not necessarily those of the National Science Foundation. So the outline, I will give a general motivation for the general problem. Then I will talk about rebel agents, the original conception, an example, related work. Then I will talk about goal reasoning, in particular about goal-driven autonomy. Then I will drill into one of the topics of goal-driven autonomy called expectations, and I will use that to explain how could we build rebel agents with goal reasoning. Then I'll make some final remarks. So let me talk about motivation and research question. There has been a lot of concern with AI reaching this critical point that is become self-aware, and there have been many well-known people who have expressed concerns publicly about that. So that's one dimension of concerns with AI. There is a second, more immediate and perhaps more practical one, which is we have more and more autonomous platforms, and they are becoming more common. And as a result of that, we are seeing more and more accidents. The accident with Tesla has been well reported. And in fact, they have been going on, these kinds of accidents for many years. There's an article from New York Times from 2014, I mean, almost 8 years ago, with a long list of accidents and things that happen. And this is not limited to actual physical robots. Our virtual robots are can be faulty. A few years back, there was a false Twitter feed indicating that there was some White House explosions, in many of these automated traders pick up on those news and start selling, and they cause a flash market crash. They had to stop the trading and reset everything. And these were automated agents that caused the problem because of this false news item. So the general research questions in AI, and at least one part of AI related to agents, is whether we can create agents that are aware of their own limit or boundaries, what is called self-assessment. They recognize when the agents have a step out of those boundaries, what is called self-diagnosis, and they act to bring themselves back into those boundaries, what is called self-correction. So this general area of research on rebel agents could be seen as an instance addressing these general agency research questions. So I'm going to move to the next topic of this presentation, which is rebel agents. This is a topic coined by a PhD student former PhD student of mine, Alexandra Coleman. There she is, her picture. When the first time that she mentioned to me this term, rebel agents, I honestly dislike the term, because when I hear rebel agents, I'm thinking about things like Battlestar Galactica or War Games or Terminator, where the agents, the AI acquire conscious, and then they rebel against the humans. And that was the connotation that I thought with the word rebel agents. But Alexandra quickly explained that that's not the case. That was not what she was thinking about when she thought about rebel agents. And basically what she was thinking about is the following. She observed that in many games, the character there are these non-player characters that interact with the player or the player's avatar, and they are very one-dimensional in the way they interact with the player, and she wanted to create agents that are more sophisticated, that are not so rigid. And to exemplify this, what she calls compliant agents, what they do, here is an example from a game. This game is called World of Warcraft. On the right side, you see somebody giving the back to us is the player control character. And on the left side, you see this white tiger with stripes. So the white tiger is this companion of the player. And basically the behavior is very simple and can be, there are all of these buttons that you see at the bottom of the screen. They may look complicated, but for players who play this game, is second nature. There is one button that the player clicks, and basically that button will tell this NPC, this tiger, to go into passive mode, meaning only attack an enemy when ordered. There is another button that the player can choose where the tiger will attack any enemy which is on site, and they are in betweens. But there is fairly linear in what the character can do. So the concern here is, can something be done where it's more sophisticated? So the idea was these rebel agents are performing actions or goals assigned by the user. But there are two key components here. One is that the rebel agent has its own internal motivations. So motivation is something that is a function of the character traits, short-term, long-term memory, social relationships, and others. And I will show you later a specific situation where goals are used, the relation between goals and motivations. But abstractly speaking, for now, the motivation is a function of all of these features. And the point is that the agent, this rebel agent, and the term rebel refers to the agent refusing to perform an action that is in conflict with the rebel agent owns motivation. That's basically the source of the conflict in the rebellion source of the source of rebellion. So let me give you an example in a game. This is not a rebel agent, but it's the kind of behavior. The difference is in this game is hard-coded. So we would like an AI capable of doing this hard-coded behavior, but it's a good example in terms of ideally something that will let us run it. The game is called Neverwinter Nights. It's a rather old game, but the game has an alignment system for all of the characters in the game, including the non-player characters and the player. So they have this alignment that could be lawful, neutral, or chaotic. And there's another alignment called good, neutral, or evil, and then combinations of the two. So then the character could be lawful good, or the character could be chaotic evil. So they have 9 possibilities depending on the player's actions. So these non-player characters that the player can hire to join them in their adventures, they have a pre-assigned alignment. So you can basically hire one of these NPCs using currency from the game, and this character is known to be lawful good, for example. When the player is playing the game using his avatar, all of the actions have particular consequences in terms of this alignment. So the typical situation is the character is wandering the road and finds somebody who is hurt an NPC that is hurt, and then the character helps the NPC get back on his feet and heal this NPC, then those actions from the player will increase the lawful good points. Whereas the player could have chosen to actually steal things, taking advantage that this NPC is hurt, take advantage of that and steal some things from that character, in which case it would be evil or chaotic evil. And the point in this game is that as the player is making these choices and is getting an alignment itself, then the hireable NPC may leave the avatar if the alignments are in conflict. So if the player hires an avatar that is lawful good, but the actions of the player help or increase their chaotic evil alignment, then eventually the non-player character will leave. So that's a kind of an example. Is there's no goal reasoning, there's no AI, everything is hard-coded, but it's kind of an example of this kind of behavior that is ideal. Now, let me say that there is a number of related works very broadly, and I didn't put any reference on purpose. I didn't want to leave anyone out. There is a wonderful overview article by Alexandra and David about rebel agents, where they talk about dimensions and types of rebellion and sociocognitive dimensions of rebellion. The topic of AI and safety, of course, has been a recurring topic for a number of years already. There has been work on endowing machines with ethical capabilities and embedded safety mechanisms into AI systems. That is something that has been studied a lot. Even longer is this theme of error control and control theory, error correction and control theory, particularly in robotics, but in general, control theory has been there for a long time. And there has been substantial research on particular robot navigation tasks on all kinds of platforms, land, air, and water vehicles that is safe. So a lot of research on that topic. And today we saw in the Body Talks, I wasn't aware of that work. It was nice to hear that on obedience and robotics. The difference versus, or the contrast versus rebel agent in those works is that rebel agents explicitly reasons about goals, and they reason about the agent's own motivation. So these two factors they have a contrast with something like control theory. So let me move to goal reasoning. The goal reasoning process, and this is a quote from the paper from David at the AI magazine, is the process by which intelligent agents continually reason about what goals they pursue, which may lead to a goal change. And there are a number of fields that are interested in goal reasoning, cognitive systems, planning, cognitive architecture. They're all interested in that. Now, it's important to realize that goal reasoning is not the same as planning. So in particular, just to ground a little bit the discussion, let's contrast goal reasoning with replanning. So the idea of replanning is, I have some goals that are given, the agent generates a plan to achieve those goals, and then they start executing those plans in the environment. At some point while executing that plan, the agent encounters a situation that doesn't allow the rest of the plan to be executed. Then a replanning agent will generate a new plan from the current situation to the goals that it had before to continue the execution of that new plan. In contrast, in goal reasoning, when that situation is encountered, it may generate new goals altogether. So not only new plan, but also new goals altogether that may happen. Having said that, making the distinction between goal reasoning and planning, is obvious that complex planning components will benefit goal reasoning. After all, once the goal is formulated, you need a plan to, you need to be able to generate a plan efficiently. Let me talk about one variant of goal reasoning, which we have worked a little bit over the past years, called goal-driven autonomy. Goal-driven autonomy is a reflective model of goal reasoning that controls the focus of agents' planning activities. This goal-driven autonomy, or GDA, controls the focus of the planning activities by dynamically resolving unexpected discrepancies in the water state and formulating new goals. And it's intended for situations where we have partial observability, you have multiple agents interacting in the environment, there are stochastic outcomes in the actions, updates occurring in the environment are dynamic, and therefore you need to change the goals over time. So that's motivation for that. So I'm going to show you the goal-driven autonomy mechanism, but first, let me show you a quick demo of an actual goal-driven autonomy agent. This is developed by a PhD student called Wei-Han Yuan, using MIT's Maritime Autonomous Lab MUS UUV simulation. So what you're going to see is this screen. There are these, let me see. I don't know if you see my cursor. Did you see my cursor or no? Probably not,
Yes,
right?
we can.
Yes, you can.
Oh, you can see it. Okay, perfect. So then in this part, I'm showing these yellow items are transport vessels that we need to protect. And they're going to be traversing from left to right in this map. Then you have this REMUS, which is a UUV, underwater unmanned vehicle. And this yellow area that is seen is basically what the UUV can see. So everything outside is blind for the UUV, so you only can see this part of the information, detect mines within this range. It may see these other boats, but mines can only be detected within this area. And there are 4 additional vessels in this scenario. I call them with these Greek letters, but the point is, each of these vessels, they could be, fishing boats, so just not hostile. But one of those may be a mine layer. This guys as a fishing boat, and it puts mines to try to sink as many of these boats as it can. And basically what this boat is doing is start by default with a goal to navigate or patrol this region. And when they encounter discrepancies, and the typical discrepancy here is when it says observation of nearby mines, then that triggers this goal-driven autonomy process, which I'll explain later, and detect a mine, and then, for example, decide whether they will going to try to clear the mines or try to identify which of these is the mine layer. Okay. So here is the demonstration. So I started the video. Here is the unmanned UUV. Here are the boats. This is obviously UUV doesn't know that, but this is the mine layer, and it's putting mines here. The UUV is moving in this direction, and it has put these mines here. And obviously the UUV doesn't see the mines unless it's very close. Now you see the mines, and it starts removing them, and it changes goals as a result of this discrepancy in trying to find more mines. Then this behavior of this boat is suspicious, and therefore the REMUS or this UUV starts a new goal to intercept this UUV. These other boats are fishing boats, and it's trying to intersect it. It intersects these boats and neutralizes it, so these mine layers is neutralized. In the meantime, these boats are moving, and unfortunately, 2 of those have been caught by mines and sink. The other ones continue, and then the UUV continue moving, go back to the original place where it found mines, and it would try to continue disabling them. So it has this stack of goals, if you want, based on what is happening. So that's a basic, simple demo of this goal-driven autonomy system, and I will use that behavior to explain the components of the GDA model. So let me start the animation, and move to the next one. Okay, perfect. So this goal-driven autonomy GDA, this is the main cycle, and I want to acknowledge Mal Molino and David Eha for the original model. So you have the agent, in this case, the CUB, is performing these tasks that I'm going to explain in a moment. First, the agent will generate a plan for a goal. So initially, when the environment starts, the goal could be a default goal like patrol. So this is a goal that is patrol. Initially, when you start, you give it to the plan, and the plan will generate a plan, which is to patrol with these expectations. And the expectations in this case are there are no mines in the area, and then the UUV start navigating following that goal of patrolling. And then at some point, it will find a mine. So that's called a discrepancy. The discrepancy detector compares the current state versus the expectation. When the expectations are violated, then a discrepancy generated. In this situation is it encounters a mine. Then trigger the rest of the process. You try to explain the reason for the discrepancy. And in this case, you generate an explanation by this module indicating that there is a mine layer operating in the area. And when the acceleration is generated, then the goal formulator formulates a new goal, which is, for example, seek and neutralize this mine layer. And that's basically the cycle, and it will continue repeating itself, generate a new goal, generate a new plan, and keep looking for discrepancies between the expectations of that plan and the actual state that is observed. So let me, just to ground even more the ideas, let me talk about the expectations in a little bit more detail. We have done a few works over the years on this topic. So let me explain a little bit more detail how these expectations are formulated, because that will help us understand the ideas that we have to construct these rebel agents, and the expectations is a key part of that. So, so the basic, I'm going to give you a few different kinds of expectations. So the intent of the expectation is to identify plan inhibiting features during plan execution. So something that will result in the plan not being able to execute it. So we are assuming we have this is the plan that was generated for some goal. So far, these are the actions that are executed before. So far, this is the last action that was executed, and there is already part of the plan that the actions that will be executed in the future. So we are in this stage where we have executed this plan and this action, and we're going to execute the next action here. So the first kind of expectation from the literature, we call it immediate expectations. If this is the last action that was executed, then they will look at the effects of that action and the preconditions of the next match the state of the world. That we call it immediate. They're looking at the preconditions and effects of the actions. There are state expectations. So if you have the initial state here, using the action model, you can project the state forward. This is the expected current state, and you can match whether this expected state matches the actual state of the world. There is, from the literature, goal regression expectations, where you look at the part of the plan that still remains to be executed, regress the necessary preconditions to execute that plan, and if those necessary preconditions are valid, the agent knows that the rest of the plan can be executed. Another student called Dustin Dannenhauer, he created a new kind of expectations that are called informed expectations. Is related to regression, but it's the opposite, because instead of accumulating preconditions, this is accumulating the effects of the actions so far, and make sure that these accumulated effects are still valid. Then I have another student who did two things. One, he introduced a new kind of expectation called Goldilocks. There is a story for that, and you want to ask me later. But the Goldilocks combine the informed expectations and the regression expectations. And he also his contribution was, I have talked about the plan, but actually he also defines expectations for policies. For the rest of the presentation, I'm going to focus on plan, but be mindful that there is a way to define expectations, even if your solution is a policy like one that reinforcement learning agents will be able to generate. So the general takeaways, I don't want to get into too many details of expectation, but generally informed expectations, the one that move forward, they guarantee that they will have, if the actions have some cost, they will guarantee low cost. Because they're moving forward, they will be able to accumulate how much cost has been consumed, and it will be able to detect issues concerning with cost. Cost, for example, gasoline consumption. If the robot has a leak and is consuming more gasoline than expected, informed expectation will detect that. On the flip side, they are not able to execute, to detect execution failures for future. Goal regression does that. It will prevent execution. It will prevent execution failures from the future, but it does not consider cost. So the idea of Noah of Goldilocks was this kind of expectations where it looks at low action costs and also prevent execution failure. So there is that. This is a nice schematic showing the different kinds of expectations. What I want to point out is that these expectations can be computed automatically given the plan or the policy, the state, and the action model. If those things are given, then all of these kinds of expectations can be computed. So this is important for what we're going to discuss later. So let me move to this part of the presentation. I'll give you some ideas for constructing rebel agents with goal reasoning. First, I want to revert back to a work that David A. and Mark Wilson from the Naval Research Lab and myself, we did a few years back. And the reason I'm coming to this work is that I promised that I was going to show you a concrete instance where goal reasoning and motivation, show you how we implemented that. And here is one concrete instance. So in this work, we have three different motivators. And these motivators are used to choose goals. So there is a social motivator. And in this case, are the user provided goals. So we were working in a version of the transportation domain. In case you don't know, this transportation domain typically is we have some trucks and they need to deliver packages between locations. And you may have a user provide goal such that, for example, the user wants a particular package to be transported to a particular location. So that's the social motivator trying to keep the user happy that his goals are being achieved. But there are other two, for the other two motivators that the agent intrinsically have. There is another one called an exploration motivator, where the goal is pursuing preferred goals that expand the agent's knowledge of the world. So we are working in an environment where the agent only has partial information of the world. Imagine that it's interacting in a location. It doesn't have a map of the different locations. It doesn't know the roads. So then this explorative motivator encourages the agent to select goals that will find more about the map and basically identify the location it's operating. So that's the second motivator. And the last operator is what we call the opportunity motivator, where the goal is to maximize the agent's opportunity to act. So if he has, excess of available resources, then this opportunity motivator will trigger, and it will try to select goals that will maximize the opportunities to use those goals. So for example, perhaps there is a longer, it has to go to a particular location, but there is a longer path to do, but it has a scenic part, and therefore it will take the longer path as a opportunity motivator. So these are three different motivators. And they're basically pointing to different goals. So the question is, how do given these motivators, how this goal reasoning agent will select among the goals? And the way we model this is we define the fitness of a goal, which is basically the score of how desirable is a particular goal. And presumably will, in a particular situation, we'll pick the goal that has the highest fitness score. And it's a weighted function of the fitness motivation of the expectations of the agent. And I explain what expectations are based on the goal that if you pick a particular goal in that particular state. And it's a weighted function where the weights are a function of the states, and there is a function we call the urgency of the state, which is a value between 0 and 1, indicating for a particular state what is the urgency relative to the social motivators. So, for example, if it's running out of gasoline, then the opportunity motivator will have a very low weight, and perhaps the social motivator will have a higher weight, and so forth. So, here's that. And there is a number of experiments that we did in this paper, and you're welcome to look at them. But the main point was the agent exhibited a preference towards social motivator goals when most of the state is observed. So you say and the resource capability is low, so it's running out of gasoline and it knows most of the map, then it will try to keep the user happy. On the other hand, if most of the state is hidden, like when the start of the scenario and the map is hidden, then the agent will kind of prefer this exploration motivator. And when there is a large resource capacity, then it will prefer these goals of opportunity motivator. That's basically the idea. And the whole point I wanted to mention this was because this is a concrete idea of linking goal reasoning with these motivations. This is one way to do it. This was Mark Wilson's idea, and this really works. It's a concrete sense on how to do this. So let's talk about now. So we have this goal manager that explains how we will select these goals using these motivators. So one of the idea is, well, why don't we try to make the whole GDA cycle using these what I will call, for the purpose of this presentation, motivation expectations. This is one of those ideas that I'm throwing out here. There is no implementation for this. So we could define an state fitness, the fitness of the state as again, a weighted function of the fitness relative to that particular motivation of the state, weighted by the urgency. And then if this fitness for a state that the agent finds itself is below a particular threshold, then at that point you will say, the agent will say, oh, there's a discrepancy. I don't want to be in this state. Let's generate a new goal. And I know now you're expecting me to tell you how will I define these others. Unfortunately, let me disappoint you that is not, it's not clear how we will define discrepancy here. I could pass the state, but as we have found that if you pass the whole state, that's too much information, and it will trigger a lot of goal reasoning this cycle. So you want to pass better information than the whole state. How would you define the explanation generator? How do you define this explanation here? So these are things that are not clear how we want to do. If you're looking for a PhD topic, here is one for you. So that's one idea. The other one is what I call, for the purpose of this presentation, directive expectations. And basically, I'm going to mimic a work from Dustin using this. So this Dustin created an agent called Luigi. And Luigi combines GDA, the GDA cycle, with description logics. So the way Dustin defines it, say we have facts, these are triples. If you have seen semantic web or description logic in particular, these are facts are expressed with these triples. In this case, unit 5. Also, this is a real-time strategy game. So there is a unit that you're controlling, or one of the players is controlling, has the property, has position, and this is the XY coordinates of this unit. So basically saying this unit number 5 is in this location in the map. Then we have an ontology with a collection of axioms. This action says, so you have a map in the game that is divided by regions, and there is a property called contest region. A region is contested. A region is contested if you have a player that have a presence in that region that's defined by an interaction, but it basically means you have at least one unit in that region. And you have another player different from the first one that also has presence in that region. So when that happens, this is a contested region because you have a presence from at least two players in that region. So there are many rules of this form. Then a state is a collection of facts like this one. So the location of all the units, the types of units, and so forth. And the inferred state are all of the facts that are inferred from the state and the ontology. So contested regions and other things that's the inferred state. So then Dustin defines the expectation will be a collection of facts. So when you click an action, there is a collection of facts that will happen. And a discrepancy happens when you take this expectation, put it together with the inferred state, and if this union of these two is inconsistent, then there is a discrepancy. You're in an inconsistent state, and that will trigger the goal-driven autonomy process. So here is an example of that from Dustin. So you have information about the state. For example, player 0 has a unit, soldier 1, and soldier 1 is in region A. Player 1 has a unit, soldier 2. There is a typo here, soldier 2 is in region A. So these are facts from the state. From this fact, one can infer that player 0 has a presence in region A. From this fact, one can infer that player 1 has presence in region A. From these two facts, one infer that the region is contested because both players has presence in that region. But the expectation from the action that we execute, perhaps we send a number of troops to that area, we expected player 0 to control region A. There is another rule that indicates these two are exclusive, so one can happen but not the other one, and that will basically trigger an inconsistency. The nice thing about this is that by using these description logics, then one will be able to generate explanations because one will look back at the trace and see what is the reason why this inconsistency happened, and then one will trigger goals accordingly. In this case, one will try to eliminate all of the units from player 1 in that location. So the player truly controls the region, is no longer contested. So this allows a very precise definitions for explanation and goal generation. I don't want to get into that. I just want to point out that you can, this description logics, then one could have the directive expectations same as before. You have the facts, the ontology, the state, the inferred state. You have expectations, but now you could have these directive expectations, D, which are generated from motivations. And then you can define a directive discrepancy when the inferred state united with this directive expectations is inconsistent, and therefore there is a violation to the agent's own beliefs and own motivations. So there are a few considerations here. We could define, for example, a state directive discrepancies. That happens when I look at the current state and I look at the directives that are given, that are part of the agent intrinsic motivations, and I put them together and it's inconsistency. Here is an example of that. Maybe the agent has received the directive that there is an exclusion zone in that area where this UUV is operating, and the UUV should not be in that area. In this kind of discrepancies, we'll detect that. We will detect that the UUV is in this exclusion zone. It should not be there. That's a violation to the principle that this agent or motivation that the agent was created with. We could imagine doing what I call dead reckoning directives. So if we have the current state and we have the plan, we could project forward what will be the expected state. And we could detect that at some point in the future, we will be in a state S prime, such that the inferred state from S prime united with D will be inconsistent. An example of that is with the current trajectory, this UV will be reaching the exclusion zone. So I could predict in advance that before that happened. And I could do something like correction, a goal reasoning style, which is formulate a new goal such that the UV will perform this goal and it will avoid this state. So that sounds simple enough, but actually it opens a number of issues. Coming back to the paper from Alexandra and David, here you're kind of wrestling control from the user, right? So the user has told you to go to this goal, and then you're projecting this, and you decide that no, I'm going to do that. I'm going to formulate a new goal. But what happened if the user was actually wanting to get very close to this boundary? It actually, the user didn't want to get pass all the way, and you're wrestling control for the user. So there's these socio-cognitive dimensions of rebellion that are really challenging, because if that happens, then the user will lose trust in the system. So then there is a question of how to do that. I honestly wave my hand here. I say, oh, you generated directive expectations from the motivations, but I didn't explain how, because I don't know how. So all of these combined is really an interesting potential PhD topic. If you're looking for one, here is another topic. And the last one, we cannot have a research talk without talking about deep learning. So the last potential topic that I would like to suggest today is deep rival agents. And for that, I'm going to borrow an architecture called HDQN, developed by Tenenbaum and students. The architecture is called an HDQN. It's a deep learning architecture, consists of 2 layers. Each of these layers is a deep learning. And the way the architecture works is operating in an environment. Is looking at the environment. So in most simple form is you can receive the state. Based on the state, it will select a goal. So the goal is selected as a function of the state. Ignore the I part, that's for something else. I'm not going to go into that detail now. It's the goal as a function of the state. So the goal selector receives as input the state. Yes, potential input side, and it will generate the next goal. Then it passes control to the actor, and the actor will basically take actions based on the goal and the state. It will take the actions until you reach a state where the goal is achieved, and at that point, it will give back control to the goal selector. So we have analyzed this architecture and other architectures that's work by Weyhan, where we map goal reasoning in general to this architecture. I'm going to do a small paraphrasing here and go to the GDA model and just observe the mapping between the two. So in GDA, you have this goal formulator. That's what this goal selector is doing. In GDA, you have the action performing when this goal is achieved. That's what the actor model is doing. In the original implementation from HDQN, the actor will cede control to the goal selector only when you achieve the goal. But there are other implementations. For example, there are a number of steps are executed and then you go back control. So there is no reason why one could not build a discrepancy detector that has this. We're looking at what this actor is doing. And when there's a discrepancy, then it goes back control to the goal selector. The architecture is amenable to that. We have our own implementation. It's really simple to do these kinds of things. But of course, if we do that, then there is a question of, okay, so what is exactly the discrepancy? How do you build an explanation generator in this context? Remember, these are neural networks. And you need the explanation, how is that passed to the goal selector? So there is some research that needs to be done. Another potential topic for a PhD. With that, I come to an end. I want to point out that rebel agents have motivations, and these motivations will inhibit itself from performing actions, even when the user tells to do those actions, if they're inconsistent with those motivations. So that's the point of these rebel agencies. They formulate goals to remedy those inconsistencies. That's another characteristic. Of course, many other research has been looking over the years, like control theory on self-correcting systems. Here, the main distinguishing feature is these goals that are used to do that. And we discussed 3 potential directions, the directive embedded, the motivation based, and the deep rebel agents. And with that, thank you so much for your attention.
Thanks, Hector. Greatly appreciate your talk. It's interesting to see the directions that you're encouraging here. So, yes, Ben, go ahead. I see you have a question.
I was just clapping.
Oh, sorry about that. Sorry.
I could ask a question, I guess.
Yeah, go ahead, please.
I guess especially in this goal-driven autonomy framework, which I've sort of seen before, but I don't know if everyone here has seen before. I'm curious, especially when we start getting towards the disobedient part or the rebel part, how tied is the action of disobedience or that rebellion to that sort of goal library that is part of this framework? Like, is the disobedience meaning I'm achieving some other goal than what I'm directly doing it? Or is it at some point saying, none of these rules apply and I'm going off somewhere else completely on my own? I'm kind of curious your take on that.
So the simple form, and here is the goal-driven autonomy framework. So the agent has its own beliefs, motivations for what to do, and then in this context, the user has still either a goal, and the agent generates a plan, or the user has still an action to execute. In the context of these rebel agents, the discrepancy happens between the action that either result of the plan achieving the goal or the action that is given by the user. Either way, from the user-generated directive that is in contrast with the agent own motivations. So this is what will trigger the process. And it will trigger the process that will result in the agent performing a new goal, generating a new goal, which would result in a new plan, basically wresting control from the user. The example that I mentioned was the one where there is this region. The agent is the user is telling the agent, go to this region, and the agent is going to the region, and then when it reaches the region, it found out this exclusion zone, so it's against its own motivations, and at that point, you would generate a new goal to basically get out of that zone. So the reaction in the way this was originally conceived was for living a new goal to fix whatever problem was with the motivation. The goal could be as simple as shut down, right? So one of the examples that David mentioned in his article, and I don't know who did that, but I was showing the example of there's this painting brush, and then if it's pointed to a particular area and press the hand, then it will spray the paint. But if it points somewhere else, then nothing happens. And that's basically shut it. So the goal in that case is shut down, or it could be something better in this case of getting out of that region that's previous. So it's a long answer to say for these rebel agents, the reaction to a violation of his own motivations is to formulate a new goal and act to achieve that goal.
Awesome, thanks.
Right. So Hector, you pointed out that one of the possible future topics could be on generating motivations generating directive expectations from motivations.
Yes.
And leave open the how that might be done. And I'm wondering what are some of the challenges that you see in this? For example, is this an issue of trying to control the size of the space that are explored for of possible directive expectations? Go ahead. I'm sorry.
No, I'm sorry, I interrupted you. Okay, so the issue is the following that I see. So the work that you and Mark and I we did on these kind of fitness functions. These are really nice to as numeric values. The issue is that for these models, these are all symbolic. So you need to pass the collection of atoms or subset of atoms that is causing the discrepancy. The explanation is also a collection of atoms. So there is a gap here between this numeric value indicating this state is not desirable because my fitness function is telling me that it's a low threshold, and what are the actual features in the state that I should pass at the discrepancy. I could pass the whole state, but this is what I skimmed through that very quickly. But when you have a state expectation, you have you pass the whole state, then what will happen, and this is work that actually does indeed for this, is that it will cause any failure that happens related to the state, it will trigger the GDA process, even if it has nothing to do with the plan. So if I am moving in a particular trajectory and I expected, I knew from the state that it should be a clear sky, and somewhere it started to rain. It doesn't affect my trajectory because I'm moving, but it's a change in the state. I have to trigger the process.
Right.
And that's the problem. So the issue here that I see the difficulty, and this is really a challenging problem, is yes, I can do these numeric computations. Oh, I don't know where I went. I can do these where is that? Here. I can do these kind of numeric computations, detect that this is the state is not fit, but then for the GDA process, I need to pass some subset of the features in the state, some atoms in the state to trigger the whole process. I should not pass the whole state because that's kind of not useful. So that's the challenge.
So I keep thinking that what's missing here is a model of attention that focuses you on a subset of either the motivations or the state or a combination of them or recent history, things of that nature, to prevent what I think you're getting at is irrelevant information being generated by this process.
That sounds like a really good possibility. If in the demo that I was showing for the UUV, it has only a small range of area that it can see, and maybe if it's only that information as opposed to the whole state, then there is something that can be done with it, because that will be really a subset of the features. So that sounds really reasonable to me, that to add to this model the focus of attention, so it's not looking at the whole state but a subset of it naturally.
Got it. Thank you. Okay, any other questions from the audience?
Yeah, I would like to ask a question. Following Dylan's talk earlier today, he talked a lot about the use of metrics and how once you give a machine learning algorithm a metric, it might interpret it in a way you did not expect it, and how that causes the value alignment problem. And it seems like this fitness metric is, in a sense, the point of this metric is to bypass this problem, because this metric tries to encapsulate something slightly different in a more abstract level. It does not measure a reward, but it measures how much you are consistent, in a sense. I wonder if it can also happen here, that we get some misalignment because we are too consistent with something that we are not. Like, could it be that the way we engineer this or formulate this will cause the reasoning process to go awry?
This is an excellent point. I'm not sure that because of the reason that you stated, I'm not sure that the fitness function will will cause that problem. But let me show you one where it will match nicely in the wrong way what I was presenting. I mentioned this part about these directives. That is what he was warning today, right? You give these directives these are user-defined directives, and maybe it will cause some problems with the agent trying to, if the directives are not properly formulated, then it may cause problems for the agent to act in a way that is useful. So I think that, as you pointed out, this kind of formulation might obviate that problem, but abstractly speaking, having a collection of directives may trigger that kind of issue. The one thing is, and it was a wonderful talk. I'm thinking that the whole paradox was based on the fact that there was a reward function. I guess one issue that I was thinking is how you define that reward function, and whether the environment has a reward function, then you would trigger that. So I do agree that a subset of these, where I have the directives and I have a explicit reward function, will lead to those situations. But if you have something like the fitness function, you probably don't. But good point. I was thinking about that myself. I was like, wait a minute, but why I they encountered, and then I think that this is why, because we are seeing these fitness functions.
Yeah, thank you.
Any other questions from the audience? Okay, well, if not, Hector, thank you very much for the presentation. Greatly appreciate it. It's great to see this
Thank you.
looked at again from an even further perspective than I have done before.